Welcome back everyone. In this video we're going to be talking about how we can compute the distance an object has traveled if we're given its velocity over time. And you might recall that if you're given the position of an object, taking its derivative will give you its velocity. And so now we're talking about how we can go back the other way. If given the velocity, can we determine the position of the object? And distance traveled is equal to velocity times time. If I know how quickly an object is moving for a certain period of time, I'll be able to compute how far it traveled. As an example, if a car drives for 5 hours at 50 miles per hour, then the car drove 250 miles. We got that by taking the velocity, which is 50 miles per hour, and multiplying by the time, which was 5 hours, to get 250 miles. And in this problem, the velocity was constant. It was always 50 miles per hour. But what if the velocity is not constant? What if it's changing over time? It's no longer as simple as just multiplying two numbers together to get the distance, because the velocity is going to be many different values at different times. Let's say that someone drove for 8 hours and they kept track of their velocity every 2 hours. And they wrote all those numbers down in this table here. So at the start of their trip they were going 20 miles per hour, after 2 hours they were going 30 miles per hour, and so on. And clearly the velocity here is not constant, it's changing over time, and we don't know what the velocity is at every second, but we at least have a rough idea of how fast the car was going at different parts of the trip. Let's break this trip up into smaller time intervals to try and compute the total distance traveled. Now let's start by going between the start of the trip and 2 hours. So from t equals 0 to t equals 2. Now we don't know the exact velocity at every second over that 2-hour period, but we know that he started that time period going 20 miles per hour, and he ended that time period going 30 miles per hour. So both 20 and 30 would be decent estimates for the velocity over that time period. Now I don't know which of these estimates is better, but let's just pick one. Let's pick 20 miles per hour to represent the velocity of this car over that time period. Now of course it's not going to be exact, but we're just using this to estimate the distance traveled over that time period. So from time equals 0 to time equals 2, the distance traveled was about 40 miles, because that was a time frame of 2 hours, and we're using 20 miles per hour as an estimate for his velocity over that time period. Now let's do that same thing for the other time intervals as well. Let's say between t equals 2 and t equals 4. And once again we have the same dilemma where we don't know the exact velocity over that time period, but we have two estimates. We have an estimate of 30 miles per hour and an estimate of 38 miles per hour, representing the velocity at the endpoints of this interval. And I'm going to be consistent with my last one. I'm going to pick the velocity on the left side of this interval. I'm going to pick 30 to be my estimate. And so the distance traveled over that time period is about 30 times 2, which is 60 miles. Now we'll do the same thing between 4 and 6. We have two velocities to pick from, either 38 or 44 would be decent approximations. And let's be consistent and let's pick 38 because that's on the left side of this interval. And that will give us an estimated distance traveled of 76 miles because that's 38 times 2. And our last interval is from 6 hours to 8 hours. And once again, we have two velocities that would be a decent approximation, that being 44 miles per hour and 48 miles per hour. And let's just choose 44 to represent the velocity over that time period. And again, I just want to stress that this is an approximation. This will by no means be an exact answer. And now that I've computed estimations for the distance traveled over all of these smaller subintervals, I can add them all up to get an approximation for the total distance traveled. And if I add up those four results from the previous slide, I will get 264 miles. And so the car traveled roughly 264 miles over those 8 hours. And I want you to notice that for each of these computations on the smaller subintervals, I used the velocity on the left side of the interval to serve as my approximation. So from t equals 0 to t equals 2, I had two options, 20 and 30, and I picked the one on the left. And then between 2 and 4, my options were 30 and 38, and once again, I picked the one on the left. There's nothing special about that. I could have picked the one on the right, but I just wanted to be consistent with my choices. Now, when you always use the velocity from the left side of every interval, this is called a left endpoint approximation. And just to get a better sense of the actual distance traveled, let's also compute the right endpoint approximation, just so we can compare the two. And so we're going to do the same thing, but use the velocity on the right side of each of these intervals instead. So from 0 to 2, my two options that would be good estimates for the velocity are 20 or 30, and this time let's pick 30 because that's on the right side of this interval. And then from 2 to 4, our options are 30 and 38, and let's pick 38 because it's on the right side, and then the same thing for the other two subintervals. And if I add up each of those answers, I will get 320 miles, which is different than the previous answer, which is okay because they were two different approximations using different techniques. So using a left endpoint approximation, we estimated the distance traveled was somewhere around 264 miles. And then using a right endpoint approximation, we got an estimated distance traveled of about 320 miles. Now, whatever the actual distance traveled was, it's likely to be somewhere between these two different approximations. And without any more information, I'm not going to be able to get an exact distance traveled, but these two values will be decent approximations for the actual value. Next thing I want to do is visualize these two computations graphically. So let's say this function here represents the exact velocity over time. And I want to walk through those same exact computations again, but now we're going to look at them graphically instead. And so our first computation was the left endpoint approximation. And we broke up the time into four small subintervals, from 0 to 2, 2 to 4, 4 to 6, and from 6 to 8. And let's first look at the subinterval from 0 to 2. And over that time period, using a left endpoint approximation meant we would use the velocity on the left side of that interval, and that was a velocity of 20, which we can see on the graph here. And the answer to the estimated distance traveled over that time interval was 20 times 2. And notice I can represent that computation geometrically as the area of a rectangle. This rectangle I drew here has a height of 20 and a width of 2, and so its area is 20 times 2, which also happened to be the estimated distance traveled over that time period using the left endpoint approximation. Let's do the same thing for the next subinterval, going from 2 to 4. Using a left endpoint approximation, we're going to use the velocity on the left side of that subinterval, and so that's the velocity when t is equal to 2, and the velocity there was 30. And once again, we can represent that distance traveled geometrically as the area of a rectangle with a width of 2 and a height of 30. And I can do the same thing for the other two subintervals from 4 to 6 and from 6 to 8. I can represent the distance traveled over those time periods as the area of a rectangle. And if I add up the areas of each of these different rectangles, I will get the left endpoint approximation that we computed earlier. And since the areas of each of these rectangles represents the distance traveled over that time period, if I were able to compute the exact area underneath this function from 0 to 8, that would give me the exact distance traveled over that time period. Now this area here is not easy to find because this is not a familiar shape. It almost looks like a trapezoid, but because one of the sides is curved, there's no easy formula to find the area of this shape. And so for now, I do have to make do with these approximations. And notice that the left endpoint approximation happened to be an underestimate. And we can see that because the area of all these rectangles added up is less than the total area underneath this curve. We can see a couple of gaps there that aren't filled in. If we were able to fill in those gaps, we would get the exact distance traveled over the entire time period. Now let's do the same thing again, but with the right endpoint approximation. And so returning to that first subinterval from 0 to 2, let's instead use the velocity on the right-hand side and represent that distance traveled as a rectangle with a width of 2 and a height of 30. Because it's a time period of 2 hours, and we're using an approximate velocity over that time of 30 miles per hour. And of course, we'll do the same thing on the next subinterval, but for the height of the rectangle, we're now going to use the velocity on the right-hand side of this subinterval. That being when the time is equal to 4, the velocity there was 38. And so we're using 38 miles per hour as our approximation of the velocity over that time period. And the distance traveled over that time period is represented by the area of this rectangle. And we can do the same thing for the other two subintervals and get 4 rectangles again. And if we add up the area of those 4 rectangles, we'll get the same answer from earlier of 312, and that will be the approximation for the total distance traveled over this time period. And here we can see that this estimate is going to be an overestimate because the rectangles extend beyond the top of the function, and to get the exact distance traveled, I'd have to get the exact area underneath this function. And so the right endpoint was an overestimate, and the left endpoint was an underestimate. Now, it's not always going to happen that right endpoint is an overestimate or that left endpoints will be an underestimate. It just happened in this problem, and something to notice, at least. In wrapping up this video, I want to remind you that given the position of an object, the derivative of the position function would represent velocity. And what we've talked about in this video is that if we're given the velocity of an object, finding the area under the curve of the velocity function would represent its position. And so there's some relationship between the derivative of a function and the area under a curve of a function, and we're not quite ready to rigorously make that connection, but for now, keep this idea in the back of your head that derivatives and the area under a curve are related in this way.